Line 3,
Yes.
number 12.
12.
Okay. So we're on page. Oh yeah, good. Page 587. This is a really good example of. In general, if I show you a point, and I don't even tell you anything about the problem, whatever, what would you assume this 2 represents? X, right? And what would the Y? Y. That's a hard one. So in general, if I have an equation, and this equation has C and D in it, any point they give me, I'm going to assume it's in alphabetical order. That's the general, unless they tell me otherwise. Any point I'm using in a problem is in alphabetical order. This problem's a little evil that way. Because the point they give me, if you put them in the wrong place, it works. If you put a 1 there and a 2 there, it works. But what is 1?
C.
Z. And 2 is? So if you want to check this point to see if it works, you plug the whole damn thing in and see if it's true, right? So you would plug 1 in for C, 2 in for D. Is that true?
No.
No. So that point is not on this line. This point does not work in that equation. Those 2 statements are actually the same thing. If it doesn't work in the equation, then it doesn't lie on the line if I drew it. Right? Yes, ma'am.
Well, I have another question.
Sure.
Number 51, it's page 597.
Okay. 51?
Yeah.
Oh, yeah. This is your classic word problem, right? The Far Side comic. Have you ever seen the math phobic's nightmare? You go to heaven and St. Peter the Caprilli, whatever you believe in. I don't care. St. Peter says, okay, to get in here, you have to answer a question. 2 trains leave Wyoming. It's like, just shit. Just send me away. So the way this starts reminded me of that, because it says 2 cars leave Denver, traveling in opposite directions. Right? We're going to assume they're traveling in exactly opposite directions. Right? That's a twisty thing. That would be horrible. 1 car travels at a speed of 75 kilometers an hour. Let's say this is Jeff. My little brother Timmy actually lives right near Denver, so we'll say that's Timmy. Timmy's traveling 88 kilometers an hour. Right? See the reference. And of course, only Canadians really understand kilometers. It's weird. You ever go to Canada, when you cross the border to come back, you look at the speed limit signs, you're like, holy shit, that's slow. Oh, wait, that's miles an hour. Okay. You go up there, you're going 120 kilometers an hour, which is not very fast, actually. So if we leave Denver going in opposite directions, right? So after 1 hour, let me just ask you a question outside of that. After 1 hour, how far apart would we be? After 1 hour, how far will I have gone? 75 kilometers, because in an hour I go 75 kilometers. So I would have gone 75 kilometers. How far would Timmy have gone?
88.
88. So how far apart would we be? Say one more time.
163.
163, thank you, yes. So you just add these together, right? Does that make sense? Okay. And see, you can do that any damn time you want to. I know the problem wants me to figure out some specific thing, but I'm like, let me just say after an hour and just see what's happening, and that'll actually help me get the equation. So now they say, in how many hours will they be 489? So after 1 hour, I'm only 163 kilometers apart. I want to know how long until I'm 489. Now don't take this too far. Don't solve the whole problem doing this, because you could guess and check, guess and check. Guess and check ain't got a place in this class, right? This is not intermediate guess and check algebra. This is intermediate algebra, yeah.
Could you divide that 4 whatever number instead of that 1 hour distance?
There's a lot of ways you can go around using algebra, right? And that's good for like a Math 120, which is a problem-solving class, which you could take after this course, in which case algebra is just one thing you could use. We're in algebra class, it's the only thing you're allowed to use, right? So I have to set up an equation for this. What's the overriding formula that's behind this whole problem? Right? I've got a speed, I've got our rates, I've got a total distance I want to go between the both of us, right? And it's asking me how long how long until we're there. So I got a time. So what's the formula?
Time, distance.
I like that. Rate time distance. Dirt. D equals RT, right? D-E-R-T, dirt. That's not how you spell it, I don't care. D equals RT, so that's the formula behind this problem, is distance equals rate times time. Right, so what's this kind of tell me? However far I go, and however far Timmy goes, at the end I want them to do what? Add up to be 489, right? So the idea is if I can get a math expression that represents how far I go, and a math expression that represents how far Timmy goes, I can add them together and equal to 489, solve it. Right, that's the idea. That's the good that this kind of example did for me. It just gave me an idea of what was going to happen. So if you want to, I highly recommend you set up a little chart. It kind of helps you organize stuff. You don't have to. If you can do the problem without it, that's beautiful. But it's really nice because then you just kind of fill in what you know. So we got Jeff, we got Timmy. What do we know for sure about us? Well, the 49 I can't put anywhere in there because it's what we're doing together, right? So whatever this is and whatever this is has to add to be 489. You got right? So I can't put 49 in there anywhere. I can't cut it in half because did each of us go half of it? No, Timmy's going faster. He went further than I did, right? So I can't just cut it in half. So it's going to be this plus this is that. Do I know how long either of us was going? No. So that's going to be what? Beautiful. I love it. So the time is unknown. It's X. And we both leave, and then some amount of time later, we've gone 489 kilometers total. So has either one of us been traveling longer than the other? No. It didn't say I left 15 minutes early or something, right? That would suck. We both left at the same time. So if I've been traveling for X hours, Timmy's been traveling for X hours. Because we both left Denver, and then we called each other, how far did you go? I went this far. Or whatever we did. I don't know. And what do I? But the thing I know for sure, no question, is I know how fast we're each going, right? My rate of speed, 75. Timmy's is 88. So what can I put here using the formula? Distance is rate times time. So for me,
75 x.
Yes. And for Timmy,
18.
yeah, cool. Because how did we get 75 here? I said after 1 hour I would have gone 75. After 2 hours, how far would I have gone? 150. Right? Just 75 times 2. So why does this make sense then? However long I've been traveling, I would have gone 75 times that distance, right? So that little thing makes sense. That represents how far I go. Not knowing how much time has gone by. So now what do I do with these two? Like we said earlier. Yeah, 75x plus 88x has to be 489. I want to be 489 miles apart. Right? And then now it's the easy step. Now that should be easy. Just solve that bad boy. Right? And hope to God it divides evenly. Let's find out. 75 and 88, we already figured out that was 163x. Yeah, divide it. Does it go in evenly? 3. All right, sweet. And what's that mean? Beautiful. So put down the units. 3 hours later. So we leave Denver. 3 hours later, we'd be 489 kilometers apart, right? I don't know what the significance of that is, but hey, we figured out the problem. So, for example, let me give you, if you make $12 an hour, and you work 4 hours, how much money do you make? $48. If you work 10 hours, how much money do you make? And this is gross, right? This is not. Let's not bring taxes in because we don't want to go to that math. That math very often doesn't make much sense. So if I work X hours, how much money do I make? Yeah, because what do I keep doing? 4 times 12, 10 times 12, X times 12, 12X. So this is a rule that tells people how to calculate how much money I just made. So if I tell them how much time I worked, they plug it in there, and that's a rule that tells them how much money I made. Right? This is a rule that says, okay, I'm going 75 miles an hour. If somebody would tell me how long I was going, or I see how long I'm going, I can use this rule to see how far I actually went. Right? It's just a rule. I like it. But what math does is it says, leave this open. We're humans. We go, tell me, 1 hour, 2 hours, tell me. And algebra goes, I'm going to tell you. So we have to leave it as 75x. And it says, for some amount of time, this happens. Oh, shit. So we got to work backwards to figure out 3 hours, right? Algebra is all about going backwards when normally we know how much time we were traveling. You with me? And why does that? Okay. Some of you guys are like, yeah, algebra's backwards. You just said it, and I knew it. Because in real life, we're very often trying to work backwards, right? I mean, I always think about crime scene investigation every time I teach because we're trying to uncover things from observations we made. We're 489 miles apart. All right, kilometers. How much time must have elapsed? There's a dead body. Temperature is this. How much time has elapsed? Right? We're always trying to work backwards from things that we see. That's exactly what algebra feels like to me. Clues, piece together an equation to help us work backwards. And all you guys are like, well, that's one way to look at it. This weird shit. Yes?
So, because in the book it said that using a system of equations, so is that required to use more than one x? If I use x.
Oh, so yeah, this problem you could do. This problem to me.
Much more complicated if you use that one.
I know. I agree with you. Some problems are easier using a single variable. Some problems are easier using 2 variables. I wasn't even paying attention to what section I was in. But we're going to do some 9-4 systems of equations. We'll do some word problems where it actually is better to use more than one variable. Well, this is relatively easy to use one variable, right? If you want to see, let's look at what this problem would look like using 2 variables. Let's see. Well, let's see, maybe we can do a fresh problem. This is all done. Doesn't really matter. Well, let me hold off. I didn't want to do word problem, systems of equations until I talked about how to solve systems of equations first, yeah. All right. Anything else from the homework? Yes?
48, the one before that one.
Oh, shoot. All right. Well, let's hold off on that one. That's a beautiful one for system of equations. Right? That nut problem is crazy. The nut house is right. Well, we'll do that one with system of equations. That's another one I wouldn't necessarily use more than one variable for. But something like number 39, 42, those are perfect for more than one variable. Yes, ma'am?
I'm sorry. 9.5, number 35. If we have more than one values in a term, then what's the degree of each term?
Oh, yeah. All right. So, I don't know if you guys remember. Do you remember talking about the degree of a polynomial, the degree of a term? Does that sound at all familiar? A little bit? Some of you guys are humoring me. Sure. The degree, all the degree of a term is the total number of letters I see. So in the first one I see 2 x's and a y. So how many total letters is that? No, I see 2 x's and a y. So I see 3 letters. Okay. So the degree of this term is 3. It's a third degree term. Third degree black belt. This one is what? Also 3. I see 3 y's. So it's a third degree term. What's the degree of this term? 2. So it's the second degree. What kind of polynomial is this? Is this a monomial, a binomial, a trinomial? Yeah, trinomial because there are 3. I love how after that they're like polynomials. Everything's polynomials after that, right? So monomial would be a single term. Binomial is 2 terms, right? like a monocle is a single lens. Bicycle, tricycle, right? And after that, it said screw. The degree of the whole thing will be the highest degree I see. What's the highest degree we see? So I would call this, you ready? I would call this a third degree trinomial. I really, really want to get technical. I need you to understand this, but it's not a huge deal because we really don't use it a lot. If I'm talking to another math person and I want you to understand what I'm working with very quickly, I can say I've got an 8th degree binomial I'm working with, and that they already know a lot about it. It's got 2 terms. The most variables in any term is 8. Do you guys see? It's just a quick way for us to speak to each other. So we're getting a little glimpse into our weird-ass language, right? Okay, and that's section 9.5 where they talk about polynomials, foiling, and putting like terms together, stuff like that. So this is just specific terminology about polynomials. Good. All right, so let's get into section 9.4. Oh, what was the... let's see if I remember. No, all right. I'll let you guys. Oh yeah, let me talk about one thing at the tail end of 9.3 that somebody asked me about earlier. Domain. What's domain mean? I like it. All right, so that's a good start. Something about the x values. Look at him, he's right. So what about the x values? So the domain is the collection of all the x values I'm allowed to use. So let me give you an example. The easiest example is something that I'm not allowed to use something. So for example, if I had a function that looked like this. Make that different. So you know why things are happening. So if I made x a number, what kind of a thing would that be? That would be a fraction, right? What cannot happen in a fraction? What can you not have happen? What can the bottom not be? Zero. You can't divide by 0, right? We call it undefined. So I can use any x value I want to for this, except anything that makes it freak out. And this specific function freaks out if its bottom is 0. What x value makes the bottom 0? 5. So in general, if they ever ask you, what's the domain of this function? If you can say in English what the restriction is, you write that in Mathish and you solve it. So let's try this again. Let's do this technically. This is not a hard problem, but you know they're going to get harder. So what can't happen here? The bottom can't be 0. So in English, the bottom can't be 0. So what's that in Mathish? What is the bottom? What is the bottom? X minus 5. Can't be. It's an equals with a bar through, right? Can't be 0. How do you solve that? Add 5, right? Are you guys doing all right? You all look like deer in headlights. Does this sound at all familiar? The idea of domain. You should have hit this when he talked about graphing, and that happens relatively early in the Math 90 equivalent course you took before this. Hopefully that statement is true. So domain is all the x values I'm allowed to use, and I'm showing you a really good way to look at it. Say it in English what the problem is, translate that to Mathish, because math is a foreign language, so there's a translation step. And if I solve it, add 5, just solve it like you do any equation. X can't be 5. That's kind of awesome if you let it be. If I can't think of anything that would freak the function out. So if I had a function, so that function has a place where it freaks out. What if I had this function here? I kind of gave it away, but oh well. Is there anything thing about this function that it can't handle? Like this function can't handle the bottom being 0. Is there any number I can't square and then subtract 7 from it? Is there any number that would freak this guy out? Is there any number you're not allowed to square? Like you can't square 7 on a Thursday or something. Right? No, I can square any damn number I want to, right? Any number you can imagine, you can square it. I'm not saying you can square it in your head. I'm saying we are allowed to square it, period, right? And then can I subtract 7 from any number? Of course I can. There's no number I cannot subtract 7 from. Even if it's negative, it just gets more negative, right? So is there any restriction on that? Like this one. There's a restriction on this one because it has a bottom. And the bottom of anything can never be 0. There's no restriction. There's no bottom. There's no square root. What would be wrong with a square root? What can't happen inside of a square root? Can't be negative. 0 actually works. Square root of 0 is 0.
What if you had a problem like it's like the square root of the absolute value of...
Don't go there. They're not going to mix it to that degree.
Okay.
And actually that would be nice because the absolute value would make it positive and then it would work, everything would work, right? So this one, the domain would be, since there are no real numbers we can throw out,
Infinity?
the domain is all real numbers. I can't say infinity because that sounds like the only thing I'm allowed to use is infinity. And I can't even get to infinity, so I could never use it, right? So you mean like an infinite number of answers, and there they are. This one also has an infinite number of answers. It's all real numbers except 5, right? All right, how are we doing so far? This should mostly be a review, but this is in section 9.3, the very tail end of the homework. They have a couple of questions about the domain. Square roots I'll leave until we actually get to the square root section a little later this semester, but we'll do domains and square roots when we get there, and cube roots and all that kind of, all them roots. All right. Cool. So now let's get into 9.4 proper. It's the worst seat to sit in if you want to. Wow. Don't worry about that. I just busted you. Sorry. So we can solve an equation like this and actually get an answer for it, right? I mean, you can solve that equation, right? How many things are there in that equation that I don't know? There's one thing, the value of x, right? So I only need one equation to solve, to help me solve something if there's only one thing I don't know. You guys with me? Thank you. So I can solve that. The one equation for one unknown. So if I had two numbers I don't know, let's say I have two numbers I don't know. I don't know either one of the numbers, but I know some stuff about them. And this is where we really get into like that crime scene investigation idea. Right? Because what do people do that's trying to solve a crime? How many things do they not know? A lot. So what do? They go out and find as much information, as many relationships between things, which are the real-life equivalent of equations, right? Equations are relations between things. Are you guys still with me? So if you're trying to solve a crime, there's a lot of stuff you don't know. Get as much information as you can to try to solve for all those variables you don't know. So if there were two things I don't know, but I told you that they add to be 12, how could you write that in math? So I know, one thing I know is they add to 12. How would you represent that with an equation? What are the two numbers? We don't know what they are. So what are they?
X and Y.
Beautiful, I love it. I always wait for that student to look at me like, I don't know what they are, and you ask me what they are? Well, in algebra, we know exactly what they are, X and Y. So how do I write that? Cool, so there's the relationship between the things I don't know, right? Together they make 12. You with me? So in a crime scene I might be like, well, this guy and this guy, they're always together. So if I can figure out what he was, I can figure out what he was. I mean, there's a relationship between them. Do you follow? All right, so there's a relationship between X and Y. One of those guys killed somebody. But if I try to solve this, I never can. How many answers are there to this? Infinite number, right? Because for every x you can imagine, there's a y that'll make it come out to 12. You believe me? It's a good idea to believe. So give me some answers. Tell me some answers.
10 and 2, 4 and 8.
Wait, let me get some. So let's stop. Stop at 10 and 2. Is everybody cool with that, right? 10 and 2. If x was 10, y was 2, answer would be 12. Give me another. 6 and 6. I like
8 and 4.
3 and who?
8 and 4.
8 and 4. Thank you.
7 and 5.
Yes, sir. Ma'am.
I have a question. If they were both 6, then wouldn't they both be x?
I like it, but I don't know if they are. So right now, it's possible they're the same, but I have to represent them with different letters because do I know they're the same? I like it. So I don't know. At the end, the math could show me, hey, they were the same. But we're like, we didn't know. Shit, we had to use two things. I didn't know if they were the same. Right? So to cover our ass, we make it the same. It might turn out that y and x are equal. That might even be the next equation I would use. X equals y, and then that would be the answer. Because that's the only way to make them add to 12 and have them be equal to each other. You guys, once I get two pieces of information together, I can actually tease out what the two things are. So if I had 4 things I didn't know, I would need... If I had 1 thing I don't know, I need 1 equation. If I had 2 things I don't know, I need 2 equations. If I have 4 things I don't know, I need 4 equations. It's crazy, right? We won't go there, don't worry. X plus Y plus Z plus W, even though we're not going to do that. And this list goes forever.
Can you put a negative?
Sure, 112 and negative 100. If you add those together, do you get 12? I just want you to really understand why it's an infinite number of possibilities, because we didn't even put any decimals up there. I didn't feel like it. But sure, infinite number of possibilities, right? Holy shit. So what if I tell you, I'm not going to use that equal one because that would give us the... Let me say this. They subtract to be what, Jeff? Do it. 2. So how would I write that?
Minus 1 equals 2.
I like it. And why does it not matter if you call... You could have said y minus x, right? Is the order of x and y really important? They're just 2 numbers, right? Like 2 people, come with me. Well, I want to go first. No, just come with me. I don't care which one I say first. Just come with me. Shit. Right? So there's 2 numbers. I don't care which you put first. So if you put y minus x, you're still going to end up with the same 2 answers. Right? Okay, so the first way we're going to solve this. And do we have the answer up there? What's the difference here? 8. So if I would have said the difference is 8, the answer would have been 10, 2. That would have been the answer, right? Now, some of you guys should know the answer, but don't say it. First way we can solve a system of equations is by graphing them. And for some of us, that might not be an immediately obvious thing. But to me, that means you don't... Maybe nobody ever told you why we graph things. We don't do it because we enjoy torturing you. We do enjoy torturing you, but that's not why we do that. But the reason we do that is because of this. If I said, tell me all the answers to this, I am not going to choose this method. Because that method would take me for the rest of my life, and my kids' lives, and their kids' lives, and there'd just be some weird-ass scene in Indiana Jones. I'm writing the answers down. I have chosen poorly. The guy that lived forever and then go in the chapter. Screw. All right. So if I take this equation, the first equation, and I graph it, the nice thing about that is when I fill in between all the points that I use, I'm covering all the other answers to the equation, all the weird-ass decimals in the middle. That's what happens. So when I graph the graph of an equation, that's a visual representation of all the answers. It's the quickest way to tell somebody all the answers to an equation. All right, some of you guys are with me. Some of you guys look on the edge of sleep. All right. Some of you are like, stop saying some of you and just do it. All right. So how do I graph this? What's the quickest way to graph it? So let me get you all doing the same thing. Ready? You want to solve for y, because then what do I know? Good. 12 is the y-intercept, right? And what else do I do? Right, so I go down 1 over 1, down 1 over 1, down 1 over 1. Boy, you picked a really ugly one, Jeff, I'll tell you. Down 1 over 1. And so forth, forever, right? So there's my line. Cool. Okay, maybe. So then, if that's so every point whatever point that is, if my graph were better, if my scale was, whatever point that is, would work in this equation. And again, I don't know if you've ever been told that directly.
How can I get all those other dots?
Oh, just keep doing the slope. The slope will go from one point to the next point. So if I just do it, and you'll see why I did that here in a minute. Because I'm going to come in, I'm going to graph the other dude on top of this. If these are all the answers for this guy, and I graph the other dude, and that's all the answers for that guy, where's the answer that works for both, where they meet? Yeah, cool. So the graphical way to solve a system of equations is see where they intersect. So part of your homework is going to ask you to do that. Graph the two lines and see where they meet, and that's the answer. So how do I graph this dude? Let me do him in a different color. How do I graph this dude here? Good. So solve for y. So if I add y and subtract 2, I'll get there eventually, right? Is that cool? Just want to cut to the chase. So what do I know from that equation then? Yeah, the y-intercept is -2?
Up 1 over 1.
Yeah, up 1 over 1. Oh shit, here we go. Up 1 over 1. Up 1 over 1. Up 1 over 1. Up 1 over 1. That's all. That my scale sucks. Too bad for me. Up 1 over 1. I picked a really bad. Up 1 over 1. Up 1 over 1. So somewhere in there they meet. So if I come down 1 over 1.
Oh.
Just the big ass number threw me off here. Down 1 over 1. Down 1 over 1 there. They meet right there. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's see. Up 1 over 1. Up 1 over 1. Up over 1. I might do this again with a better equation. So the reason I do these multiple steps, this is horrible. Well, the reason I do these multiple steps is so that I can kind of see better where this goes. Of course, this big ass number made me have to have the scale all freaky. And the answer would be where they meet. Now look, let's see where they meet. They meet at 7, 5, 7, 1, 2, 3, 4. Let's make it 5 because that's right. 5. So I'll do another one with smaller numbers, so I don't have to make my scale all freaky. It's hard on the board. My scale just sucks. Yeah.
What type of solution would you do where not really a shortcut, but you would add?
Yeah, good. So we want to first want to talk about the graphical method, and then there's 2 algebraic ways. Yeah, because the graphical method would really suck if the right answer was 4.29, 6.83. Ain't no way I'm going to see that on my graph. Hell, I can't even see freaking the right answer to this because I draw so bad. But the answer would be 7.5, and that's where they meet. That's where they should be. But does that work? 7 and 5 add to be 12. 7 and 5 subtract to be 2. Right. Let's do one more with some smaller numbers so you guys can see it better. So if I had, for example, y equals, what you got, Jeff? I want to make it come out nice. Let's see. Ooh, that would be gross. Yeah, this will be alright. I think we can handle that. It's a lot better than the other one. Alright, so here we go. Here's the idea. So there's a few graphing problems in the homework, and they'll be roughly like this. You might just solve for y first, so you can just see the slope and the y-intercept. But very quickly we learned that graphical method only really works well if the answer is like whole numbers, right? The minute there are decimals, I got to have an algebraic way. So if I wanted to do this graphically, for the first one, what's the y-intercept?
1.
It's 1. y-axis 0, 1. And from there I go up 2 over 1. So let's do a couple of steps up 2 over 1. Here's the thing that I want to tell you right now. 2 over 1 is the same thing as negative 2 over negative 1, right? Math would go, ooh. But slope-wise, what does it say to do now? Go down 2, back 1. See, I'm still on the same line, right? All right. So some of you guys should have seen that before. If not, there it is. So here's that line. Okay, cool. Make these big. Yeah. What about this line? The y-intercept is 6. 1, 2, 3, 4, 5, 6. Good job, Jim. And then it goes down 1, 2, 3. Yay! So what's the answer?
1, 3.
1, 3. Cool. And then you can check it real quick. All right. And let me take all that out of the way. If you plug a 1 in there, you get 2 plus 1, 3. If you plug a 1 in there, negative 3 plus 6 is 3. So that is the 1 point that works in both equations. Cool. All right. This might be old news to some of you guys. I can't really read your expressions. So let's get into the algebraic way to do this kind of thing. This might sound more familiar. The two methods are substitution and elimination. Sometimes the book call it addition method. I like the elimination method. You want to eliminate one of the variables. So if I wanted to use substitution on this, here's the idea behind substitution. My first equation says y is 2x plus 1. And my second equation says y is this. But what's y? What do I already know y is?
2.
So I can rewrite this in a better way. I can use information from one guy in the other guy. So I can replace this y with what it is. Right? So most of the time people kind of know substitution method pretty well. Hopefully that's true. So you just solve one equation for a variable, and then you plug that into the other equation. And now what's nice is, how many variables are in there? 1. There's just x, so I can solve for that. Right? So it's a very subversive way. You kind of like sneak in there and replace somebody. I like elimination. It's very overt. I'm going to kill you. Right? It sounded horrible. It's too bad. So how do I, and then you just solve this. So what do you do? Yeah, add 3x. Subtract 1, so I get 5x equals 5. So x is 1. So far that's good, right? And if I plug a 1 back in, to either one of these, I get 3. Yeah. All right. And that's all there's to it. So if you don't have something solved for a letter, you solve for a letter. That's all, right? So any questions on that? Let's look at elimination. Let's do that. Actually, let me do a couple of examples of elimination because it gets a little bit more difficult. Start with a nice one. Let's see. I guess I can make it work. That would be nice. That should work. We'll find out if Jeff did that right. Yes, I did. All right, sweet. So the idea behind elimination, plus is if I can, and first off, a lot of people do this, you don't even know why you're allowed to do this. If I add 9 to this side, I have to add 9 to the other side too, right? That's a simple fact. But 9 is this. And that's why I'm allowed, if I add 9 to this side, I can add this to this side because this is 9. So I am adding the same thing to both sides. So a lot of you guys know this procedure, but I don't know if you know why it's allowed. You're allowed to do this. And why is it good if I add these straight up together? What happens? Yeah, so I like this. It's very in your face. I'm going to kill your y. I don't like your y. I'm going to kill it. Right? And it's not. If I kill one of them, then the other one's left alive and can solve for it. I got too many problems. I'm going to kill one of them, then I get one problem. All right, so these would cancel. I get 7x equals 14. Yeah, x is 2. And once I get x, how do I get y? Either one, right? And it's a good way to check. If you plug in both, it's got to agree. Because this is where it's supposed to meet, right? So if I plug a 2 in, I don't care, which one?
The second one.
Second one, okay. So you get 3 times 2 plus y equals 9. 6 plus y is 9, y is 3. So this is okay if you circle your answers, but really what should your answer look like? It should look like a point, because the answer in any system of equations is a point. So then it would be 2, 3. Kick ass. So real quick, that's how I made the problem, right? I started with the answer, and then when I wrote 4x minus y, I said, let me have 2, 3 as the answer. 8 minus 3 is 5, and then I put 5 there, and that's why I knew it would work. So sometimes it's good for you guys to see how I make problems. All right, so the only way this can get more difficult, that was easy because they were already the same, just opposite sides, right? So they were just ready to die. Poor little dudes. So what about this one here? What can I do here? What was it, Jen? Yeah, there you go. Oh, that's all right. Bless you. Thank you. This is kind of neat. I'll leave this one open. Yes?
Oh.
Go ahead. What?
Oh, no, I was going to start
Sure.
canceling out. Well, you can start, I guess, x or y, but it's more convenient for that the x because it's already, I don't know how you word it, but you can multiply, if you want to knock out x, multiply the top equation by -2.
All right, good. So the whole idea is I want to have one of these variables be the same number, just different signs, right? They currently aren't. But the easiest one between these 3 and 2, I'd have to multiply both of them to make them both 6. It's almost like an LCD idea then, right? But here, 2 and 4, I just have to make him become 4. -4 even better, because then they're opposites, they'll cancel. So if I multiply the first one by -2, I love it. If you tell yourself what you're doing, you're also telling me what you're doing when I grade your work. It's a little easier for me to get pushed around. Right? If you're just doing shit, I don't know what you're doing, I don't know. So now what's the first equation look like if I multiply by -2?
Minus.
Good. The biggest mistake is people forget that guy, and you get the funkiest answers in the world. So the whole equation has to be multiplied, right? And now, why did we do that? Because now, let's cancel when I get... Yeah, y is +1. I like it. So how do you get x? Plug it into 1. Looks good. 2x plus 3 times 1 equals 1. Minus 3. 2x equals -2. Divided by 2x is -2. Right, so that should be relatively easy solving those equations. Yes, sir?
I don't know if I saw it, but on the top equation, since you multiply it by 2, would you make, since that new equation would be -4x and whatnot, whatever, would you plug that into that equation or to the original one?
That's the same as that. These are the same equations. Believe it or not.
So you would get the same answer.
Yeah. If I do something to both sides of an equation, it's still actually the same equation. The funny thing is I'm just making it look different. That's all I'm doing. If I double both sides of something, I'm just making it look different. It's still the same exact equation with the same exact answers. Maybe. So hopefully that sounds familiar. The substitution method, elimination or addition method, whatever you called it. All right, so that's section 9.4. So let's look at some of these word problems. Let's try this one. This one sounds a lot like how I set up the very first problem we did. I'll put it up here, number 40. So it says find the two numbers where the sum is 108 and the difference is 50. So this is good. I have two numbers I got to figure out, so they gave me two pieces of information, right? Mm-hmm. So how do I use the first piece of information? And you can be creative with your letters, right? You don't always have to use X and Y if you don't want to. You can use L and W. You can use happy face and box. I don't care, right? Right? Because all they are placeholders. But now that we picked X and Y, we got to keep doing it. Their difference is 50. Kick ass. And that sounds a lot like that first thing. That's not really what I would call a true word problem. It's like one step away from the map. So then to solve this, what's a good method to use? Elimination is beautiful, right? You can use any method you want to on these because it doesn't say. Some of the homework says you got to use a specific method, and if you don't, it's going to make you redo it. So just do what it says. This one just is open. You do whatever. But these are beautiful that go away. So I get 2x, cancels, 158. So x is 11. 160 cut in half is 80. So 158 is going to be half of 2 and 1 less. So it's going to be 79. I like it. So if x is 79, don't just do this and go to the next one because the question was about two numbers. If x is 79, the other one must be 29. Cool. Sweet. And what's 79 minus 29? Sweet. See, so you always have a way to check. Use the one you didn't use. All right, how we doing? All right. You're all at least looking my direction. It's good. I can't tell if some of you are bored or some of you are like, I don't know any of this shit. All right, so let's try like a real word problem, and then we'll talk a little bit about factoring. Okay, here we go. Perfect. So number 46. So they sell paperback books. Paper books. Let's try that again. Paperback books for $1.99 and hardbacks for $4.99. Ooh, you like it already, right? Decimals and Holly recently purchased a total of 14 books. So what kind of books did she get? Exactly. How do you know? Holly just likes those color books. She got a mixture, I don't know, a mixture of the paperback and the hardback, right? So that's one relationship. But there's two things I don't know. How many of each kind of books you got, right? So they better tell me one more thing, and they do. They tell me for a total of $42.86. Total of 14 books for a total of $42.86. Yes, Jeff, yeah. So how many paperbacks and how many hardbacks did she buy? So a really good idea with this kind of this is a true word problem, really, is to use letters associated with the actual physical things. I'm going to use the letter P and H. It's incredible. You can use whatever the hell you want to. How do I represent this? And what is P and H? What do they really represent? What does P represent? What about them? No, not the price. I know exactly how much they cost. What do I not know? How many? Good. So P represents the number of paperbacks, and H represents the number of hardbacks, right? So how can I represent this first relationship, the total of 14 books? Beautiful. I love it. So one thing is P plus H. Now, what's wrong if I write this? This is what I see. Why is that wrong? Because I got number of books plus number of books equals money. How the hell? No, it's got to be money plus money equals money, right? So whatever you got here has got to actually match with what you got there. That ain't what I got there. I need some work. So how many paperbacks? P. How much did each paperback cost? So how much total for the paperbacks? Multiply, right? $1.99 per paperback. Good. Plus $4.99 per hardback gives me good money, right? So that's a quick. Just do a unit analysis. Make sure that the units match up, right? You can't say dogs plus cats equals I don't know money. So peanuts. I don't know. And then what's a good way to solve this?
Multiply -1 from -1.
Well, I tell you, this is one where I do substitution. If you solve this for P, how would you solve this for P?
P equal 14.
You're right.
Subtract.
What?
No, nothing. Equal.
We're also P equals what now?
14
minus H.
Cool. So if P is 14 minus H, I can throw that in there, right? Because the numbers are kind of gross for elimination. I don't necessarily want to be multiplying everything by 1.99. You with me? You could. There's nothing wrong with it.
You could, but it'll be ugly.
It will be a little. This is still going to be ugly. There's no way to get away from really ugly out of this problem, you know. But still, it's not quite as bad. So see what I'm doing? In place of P, I'm putting what it is: the 14 minus H. Now I know some of us would maybe kind of give up somewhere before we got here because of the numbers looking so ugly. But I mean, the basic idea behind this is easy. The numbers are gross, but who cares? Right? You can use a calculator. I don't know what you're doing in your homework, but I certainly wouldn't mind if you use a calculator on this. What's 1.99 times 14? 27.86. Somebody help me. Is that true?
27.86.
27.86 minus 1.99h. Is that cool? Just distribute. I don't care how ugly the numbers get. The process I use to solve an equation never changes, right? I'm getting kind of low there. Let me pull it up here. So what can I do here? Yeah, so negative 199 plus 499 is 3. I like it. So that's nice. 27.86 plus 3h. Yeah, minus 27.86. I like it. Trying to get the h by itself. I'm going a little bit fast here, but this is solving an equation. The numbers are ugly, but I want you to get over that. Who cares? I'm still going to do the same steps. Bam. 3h equals kick ass. And then look at that. Look where it started. So now divide by 3. H is 5. What does that mean? 5 hardbacks? So how many paperbacks?
9.
Yeah, look here. What's really nice? P equals 14 minus H equals 14 minus 5 equals 9 paperbacks. Can somebody back there close the door? It'll do a little bit for us. There's a vent in the door, but oh well. All right. I hope you guys understand. These are actually normally easier to set up than the word problems from 9.2. These are a little less vague. You have a very specific, you add the numbers together, you get 14. You multiply by the prices, you get the money. It's a little bit more focused on an idea. Bam, bam. So let that happen. That's my hope. Okay, good. Yes, sir.
You skip the voice.
Yeah.
Sorry.
That's all right. All right. Let me, let's see. Let me let you guys try one before we go into the factory stuff we're going to talk about. Maybe, oh, look at that. That's freaky. It was waiting for me. Maybe that problem, somebody asked me about this problem?
48.
And so you just got to sit there, because I know you've already tried it. Anybody else to try it? The one about the nut house? So to be honest, this one actually is a lot like the one we just did. You almost always have an equation that's a total. So it'll be x plus y equals 20 or some number, right? then in this case you have money. So try to set the equation, and before you try to solve it, we'll try to set the equations up and make sure we're on the right track.
This one and the last one, or you
Oh, for factoring? Yeah, good. You can write it like that.
Which number we do?
48. What about the nuts? Cash for your expense.
Sorry.
Sorry. Okay, all right. Well, let's see. I want to see if you can set this up freehand. I'll give you like a chart thing if you want for organizational purposes, but you should be able to set this up actually without it. Let's see. What are your variables going to represent? What about them? Be very more specific.
How much they cost?
No, we know exactly how much they cost, right? That's all right.
Kilograms.
Yeah, the amount of each. The number of kilograms of each. How much, right? So like that last one was the number of books, the amount of books, right? So, 48. Oh, real quick. We're doing that problem there. Anybody playing at home? If that was too fast, they can just pause it. So the cashews. So I can let C. Let's see if he can work. The number or the amount of cashews, right? In kilograms. And amazingly enough, P is the amount of pecans in kilograms. Alright, cool. And it doesn't matter. You can use whatever letters you want. But it kind of makes sense to use the same letter so you can kind of keep it straight between the two. So what's the first easy equation I can set up?
This is first one equals to.
Yeah, good. There's a total of 10 kilograms. You almost always have a total equation. So the amount of cashews and the amount of pecans has to be 10 kilograms total. Right? So kilograms, 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 units, check, thank God. So what about the second equation? Good. 8 per kilogram, so the total cost of the cashews is 8 times C, good. Plus 9 times P. And here's where people got to be careful. Do you see how it's price per kilogram times kilograms, price per kilogram times kilograms, price per kilogram for the mixture is 840. And how many kilograms? Good. So that's the part where people forget. So the total cost for the cashews plus the total cost from the pecans must be the total cost for the mix. 840 per kilogram at 10 kilograms. That's the total cost of the mix. So the two sides of your equation have to actually match up in ideals. Yes, sir?
Is that when you're going to do elimination?
Yeah, now you can do whatever way you like. So elimination would actually be decent because the numbers are a little bit more manageable, right? First thing is, what's 8.4 times 10? 84. Is that cool if I just do that? 84. So I don't have to write it. So what can I do? If I want to use elimination, what can I do with the first equation? I love it. You can do -8 or -9. Kill either one. If we want to kill the cashews, multiply by -8. So these end up canceling, right? So then you get, for the first equation, what do you get? And if you want to, you can put a little -8, next to each one so you don't forget to do each thing. So over here we get -8. That's really, really, really nice. That's extra nice. Because then I get,
1 seed of 2 equals 4.
so what's that represent?
Pecans in that mix.
What about the pecans?
How much?
4 kilograms.
How many kilograms? Good. So 4 kilograms pecans. So how many kilograms of cashews?
6.
Yeah, because it's supposed to add up to be 10. So 6 kilograms cashews. So whoever asked that question, when you everybody realizes it's a homework problem, you got that one done. So that one actually is a little bit easier if you use 2 variables. Right? The other ones I kind of disagree. It's easier to do them with 1 variable, the ones we did earlier. Okay. Cool. All right, so in the last few minutes here, you guys are funny. I love it. The clock moves slower. They look backwards. Someday I'll do that. All right. So what I'm going to do now, that's section 9.4. So now officially we're done with chapter 9. I just want to go back, because we talked about factoring before, but I want to go back and talk about cubes. And then we'll do a couple of just general factoring, and then we'll head out. Right? And like I said earlier, if you have trouble with factoring, you've got to focus on that. Go get a tutor, go see me. You've got to get the factoring down, because all of chapter 7 relies on that. You can't do that, you can't do chapter 7, period. So cubes. It's kind of from a request somebody had. We talked about this, but let's talk about it again, because cubes are people's most hated factoring form. And to do this, let me recall. I said we're going to do cubes, now I'm going to do squares, but just as a comparison. How do I factor that? That should be a thank God problem, or a thank whatever deity, right?
Well, you're gonna have 2
Flying spaghetti monster, whatever it is.
You're gonna have trouble with negative.
Yeah, because everything can be cut in half, right? So I do it. X squared is XX.
Minus 5 plus
Yeah, negative 25 is negative 5 and positive 5. And that's what really lets the middle term cancel. That's why there's only 2 terms, because negative 5x plus 5x cancels. So what's special about that? So this is done here. What about that? If you think it's x plus 5, the middle term would still be 10x, right? That sucks. They wouldn't cancel. So you can't factor a sum of squares, for the exact reason why you can do a difference. The difference allows these to be different signs, which makes the middle terms cancel. Shit. Middle terms have to be the same sign. They'll never cancel. I can't do that. You could actually just call this, what would you call a number you can't factor? Prime. So this would, you'd say, prime, leave me alone. Right? Is that cool? All right, so now let's talk about cubes. Squares, you can cut everything in half, you do it. Cubes, you can cut everything in thirds, you do it. All right? So let's see. Let's start with a nice one. I have x cubed minus 8. All right, so there's no GCF, right? Kind of always look for that first. It's 2 terms, so it could only be squares or cubes. There's only things that 2 terms works. And that kind of gives it away, right? Plus the 8 is not the square of something. What's 8 made of? 3 whats? 2's. 2 times 2 times 2. So this is x times x times x. 2 times 2 times 2. Because everybody wants this to be this. And I don't care what you want, because that ain't it. Right? This just doesn't work out. You'll get all this middle term shit. So this is going to be little dude, big dude. They look the same size. Let me make him big. Big ass dude. Wow. Okay. And in the little dudes, he's a little dude. You can only take 1 of each. So in the squares, I put 1 there and 1 there. In the cubes, I'm going to put 1 here and the other 2 there. So overall, I still have 3. Right? So 1 of each in the little dude, 2 of each in the big dude. So overall, I have 3. So why is the big dude big? Because here I'm going to put minus a 2. So what am I going to put at the end here? 4. That's always positive there. So why do I need anything else? That's why only math people always make things so complicated. Well, do I get what I want? I get x cubed here, right? That looks good. I get minus 8. I get minus 2, shit, I get minus 2x squared. Do I want minus 2x squared? Right? I'm checking my answer. I got to check my answer by multiplying it back up to see if I get this. I got an extra freaking term I don't want. And I get 4x here, right? I don't want either one of those. So I'm thinking of remembering, I also talk about factoring my 176 class, so I got to keep it straight. Because in there I call the middle dude is the cleanup dude. He's like that dude in Pulp Fiction. The fox is that? They had to call him and they actually shot the dude in the back of the car. Oh my God. I like that reaction. So the middle guy is the guy who's going to clean up this mess, right? So if he's going to be the cleanup dude, he's got to be the opposite sign so he can cancel this shit out, right? So one of each, two of each, product in the middle. So closest I'll ever get to singing a song about that. Okay. So what's 2 times x? 2x. And the opposite sign? Plus. So watch this, watch. The thing I just added, I get minus 4x when I do negative 2 times it. See that? Minus 4x kills that. The thing I didn't want. And when I multiply x by it, x times 2x is positive 2x squared. So it cancels that out. Let's do another one, and then we'll call it a day. Yes, ma'am?
So how you got the middle 2 and the big one, you multiplied...
Whatever these are, multiply.
Okay, gotcha.
Good. All right, all right.
Would that be always?
Always. Yeah. And the big dude, you can never factor the big dude. The middle term is actually half of what it would need to be for it to factor. So don't waste any time trying to factor the big dude. That's probably the only time you'll ever hear that sentence. Don't waste time trying to factor the big dude. So what if I had this 27y cubed plus 64w cubed? Oh yeah. Is there a GCF? No, good. 27 makes 3s and 64 is made of 4s. They don't have anything in common, right? It's 2 terms. Why is it cubes? These are kind of a giveaway, right? Can you break 27 up into 3 parts?
Yes.
3, 3, 3. And y cubed is, so it'll be 3y, 3y, 3y. That's what makes 27y cubed. You guys with me? How do I make 64w cubed?
4w.
Good. 4w, 4w, 4w. I like it. I like it a lot. So then you got little dude, big dude. That's what you put down when you got a cubes. Little dude's a little dude. So what goes in the little dude?
3y
1 3y plus
4w.
1 4w. So one of each of the little dude. What's that?
3y squared.
Careful.
9 squared.
Good. 9y squared. And see how you got to get, see this? This is 27 like it's supposed to be, right? And at the end I would put,
16.
so one of each, two of each, product in the middle.
So 12y
Good.
negative.
12wy. That's the opposite sign, and that's always positive. So here's a little saying for you. Ready? This is the same sign. See that? See that? Same sign. This is the opposite sign. This is always positive. I'm okay with that. I normally don't like a lot of mnemonic devices and tricks because then you're not really learning, you're just doing tricks. But that's okay. That's not too bad. It's a nice little way to remember how the hell to set this up. So,
Oh, yeah.
yes, sir.
So you said that is the opposite, the middle?
Yep, there's always the opposite. Why? Because he is the cleanup guy. He's got to cancel the shit I don't want, right? So he's got to be the opposite sign so he can cancel it. Cool. Like I said, that's plenty for today. So. Oh, Tuesday, quiz. Chapter 9. Chapter 9, quiz. Homework, the hard deadline for the homework is always the test. But I'm saying by Tuesday, you should be about ready to turn in Chapter 9 homework. Okay, good.
By this Tuesday?
If you haven't already. Yeah.
All the 90 questions.
Oh, yeah.
Oh.
But if you're not, you've got some time, right? But the further you are away from that goal, the further behind you are. Okay.